Morning. We were discussing transistor level realization of op-amps, and we in particular were looking at realizing the single stage op-amp using the differential pair with the current mirror load. Okay, so we know now essentially the most of the characteristics of this op-amp. So if I bias the inputs at some VICM and the output, the large signal output, the total output will be VO. We know that this the small signal equivalent of this whole thing will be a differential input VD with a transconductance, which is the transconductance of M1 or M2, and then okay. Now, if you have, as you will, some load capacitance here, and then some parasitic capacitance there, at the output, you will end up loading it with CL, and this GM1 changes to GM1 times 1 plus what? S times what in the numerator? CP by 2GM and CP by GM. This is GM3. Okay. So at low frequencies, you get a transconductance GM1. At high frequencies, you get GM1 by 2. This is because half of the current gets shorted out. Okay. So from this, you can see that the DC gain is okay, and the unity gain frequency of the op-amp by itself is GM1 by CL, and you expect that these parasitic poles and zeros would be outside the unity gain frequency, okay, or unity loop gain frequency. And as far as the large signal parameters are concerned, we have the swing limits on the input. I denote the total tail current as 2I0. Okay, and on the upper side, okay, and the total, it's assumed, of course, that VD is small because this is an op-amp and it has a substantially high gain. So that's an assumption we always make. On the upper side, it is, and on the lower side, it is VICM minus VTN. Okay, these are the large signal characteristics stemming from a limited supply voltage. Okay, so the crude way of sort of estimating the, I won't say estimating nonlinearity, specifying the limits of linearity is swing limits. There are two kinds of limits. One limit comes from the limits can come from either the supply voltage or the bias currents that you use. In this case, we are not assuming that a signal, significant load current is flowing. So basically all the limits are related to just voltages. Okay. Now, of course, in any op-amp circuit, both these limits have to be satisfied. That is, the input common mode voltage must meet the limits on VICM, and the total output voltage must be within the limits on VO. So depending on the kind of circuit you have, one or both could be significant. Okay. For instance, in general, in non-inverting amplifier topologies, you also have a significant common mode swing. Okay, so the common mode swing limit may also come into picture, right? Any questions so far? No, this is an open loop op-amp. You will never use the op-amp in open loop. You will put this in feedback, and in the feedback system, you can have common mode swing. So like I showed here, if you have this non-inverting amplifier, the input common mode will be the input voltage. Whereas if you have the inverting amplifier, the input common mode will not have any signal component. It will be fixed. Okay. Now, what other large signal limits do you expect? Is there some limitation because of the current? What happens? So we have this single stage op amp. I'll model it just by the transconductor GM1, and I have the input voltage Vi. Okay. So let's say the input is a step. Okay. What happens to the output? How does it start? Let's say the output is at some operating point somewhere. What happens initially? Huh? Yeah. So basically, initially, this voltage will be whatever it is, and it won't change, right? Immediately after the step, the output voltage still remains the same. So the entire input voltage appears across the GM. Okay. So the output will start ramping, and what will be the rate of change of the ramp? What will it be? What is the rate of change of the capacitor voltage? Current divided by capacitance. What is the current? GM1 Vi. Okay. So if you apply a step of Vp, the slope will be GM1 Vp by CL. Okay. Now, if you apply a larger step, you of course expect that you have a higher slope. Now, what happens as you keep on increasing the step size? You understand the question? So if I start with a very small Vp, the current flowing immediately after the step is applied will be GM1 times Vp. And the rate of change of the output voltage will be GM1 Vp by CL. So if I go on increasing Vp, the slope will keep increasing. Will it? So finally, as you said, the rate of change of the capacitor voltage is that current divided by CL. Is there any limitation on that current? How much current can you get out of this? How much current can you get out of this? Can you get any amount of current? What will be the limit? And when does that limit occur? Huh? Vd is 0. What will be the limit of the current? How much current can you get out of this? Extract out of this op amp? Huh? I0. Why I0? Correct. So what will be the maximum? I mean, not yeah. So what is the maximum possible? If you apply a Vd large enough, what happens to the transistors? Let's say a positive Vd that's large enough. Huh? So M1 will be, M2 will get cut off, right? At some point, we can figure out how much that is. Some point it will get cut off. So 2I0 will flow here and you will get mirrored. Okay, this is cut off. So 2I0 will be flowing there. So the limit is 2I0. And in the other direction, it's the same. M1 can be cut off, in which case M4 is not there. And then this is M2 will draw 2I0 from the capacitor. So it's the same in the positive and negative direction. In this circuit, it happens to be the same. So this limit, this is called the slew rate. You must have seen this, right? You have seen the slew rate limit. So you basically make a voltage controlled current source. There are limits on the voltages because of the power supply, and there is limits on the currents that can be drawn out of the circuit because of the bias currents. So that's what we have here. Okay. So now this also is a nonlinearity, because what happens is, what is nonlinearity? What is the meaning of nonlinearity actually? When I say some circuit is nonlinear or some system is nonlinear, what do I mean? So basically, yeah, it's related to this proportionality and homogeneity and so on. So if I double the input, I won't get double the output. Okay, whatever the output is. So because now in this particular case, if I apply, let's say, a square wave, I'll of course not get a square wave, but I'll get something like this. It depends on the Gm1 by C. I'll get some exponential rise and fall. Okay. If it was completely linear, if I double the square wave amplitude, the output will be the same waveform, but scaled up by factor of 2. But now with slewing, what happens is that initially the output will ramp up at the slew rate. Okay. And what happens after that? So let's say you apply a very large step, then one of the transistors is cut off, and the output starts ramping up at 2I0 by CL. What happens after that? As the output is ramping up, the difference voltage across the op-amp inputs goes on reducing. Okay. And at some point, the transistor that was cut off will turn on. Okay. So it goes into the linear region. And after that, it will follow the linear settling. Okay. After that, you can assume that the output is GM1 times VD, and it becomes a linear circuit. Approximately, of course, in real cases, it's not as though up to that point it is non-linear and after that it is linear and so on. The switching is soft, but this is what happens. So now what happens is that if you had an input that is half, it may have started linearly even from the beginning. Okay, so this won't be 2 times that. Okay, if it is slewing, so that also causes non-linearity. Okay, so if you look at if you normally in a linear circuit, if you look at, let's say the target is that and you settle exponentially, of course, if you don't give it enough time, there'll be some error, but it will be linearly related to the input step. Okay, so if you double the step, the error will also be double. So it is still a linear circuit. Okay, but if it is slewing, that error will not be proportional to the input. Okay, because some portion is spent in this nonlinear behavior. Okay, so that is the nonlinearity. Is that okay? So this is one of the sort of swing limits or nonlinearity limits. Obviously you will be concerned with this only if you have step-like inputs usually, and there are certain switch capacitor circuits where you expect this to happen. Okay, so if you apply sinusoids also, of course, beyond some input amplitude, the slope will be large enough, but probably you will hit the voltage limits before that. But if you have a step, you can always have slewing if the step size is large enough. Okay. Any questions? Well, that is a separate complication we will not take. Depending on the bias voltages and so on, maybe for some, let's say the slew rate is so high that the input step you have to apply to get to that slewing area already also violates the other swing limits. That is possible. Okay, that is, you have to step this up so much that this one goes into the triode region. But let's take one thing at a time. If that's the case, you will know. That's all. What is that? No. The assumption is always that the operating point is set correctly, right? Otherwise, the circuit won't work. The operating point is set correctly, and after that, you apply signals to it. I mean, for small signals, you never consider any change in operating point, right? By definition, the incremental small signal picture is that you have the picture around the operating point. That's what you use. Okay. But yeah, I mean, if you swing the common mode substantially, there is no cutoff, right? It will only that this will go into the triode region. With common mode swings, nothing will cut off. Okay. A common mode limit to which one? Again, we will not be using the op-amp in open loop, right? We'll use it in closed loop, and we apply some signals. And those signals may cause some common mode input for the op-amp and some differential input for the op-amp. Yes, it is possible that with that, maybe with some combination of parameters, you reach the triode limit before this. That is possible. What is the value of VD at which one of the transistors, input transistors, will cut off? Going out by GM. Okay. Is that correct? What is the value of VD at which one of the transistors will cut off? Or does it depend on VICM? How will you find out? I mean, yes, the 2I0 by GM is assuming a linear behavior for GM, right? Your if I plot I1 and I2, if I plot I1 and I2, what happens is both of them are equal to I0 at VD equal to 0. And if you assume a linear model, one of them will be I0 plus GM1 times VD by 2. Okay. The slope will be GM1 by 2, and then it reaches a limit of 2I0, and the other one would be the other direction. Okay. So this is, let's say, I2 and I1. Okay. Now this is assuming that the currents change linearly. Okay. But can you look at the circuit and tell me, I mean, what is the value of VD at which one of the transistors just cuts off? How do you find out? Huh? Right. So what happens is that I1 goes on increasing, I2 goes on decreasing. At the point when M2 just cuts off, M1 will have a current of 2I0. M2 will have a current of 0. So what will be the VGS of M1? So what is VD? VD is just VGS1 minus VGS2, right? This is VGS1, this is VGS2. So what is VGS1 when M1, the current in M1 just reaches 2I0? it will be Vt plus square root 2 times the current divided by, maybe my usual notation is better, Vd sat 1 at a current of 2I0. What is the VGS of M2 at the point where it just cuts off? What is it? Vt, the threshold voltage. So minus Vt. Okay. So this goes away. So the limit is basically Vd sat 1 at a current of 2I0. Okay. What is it that we had got here? You said it's basically from the linear picture you get I0 by, no, you equate, you assume that the incremental current is GM1 times Vd by 2, and that you equate to I0. Okay, that's when it switches. That's the assumption from this increment above the operating point is GM1 times Vd by 2, right? And when that reaches I0, one of them carries a current of 2I0, the other one cuts off. Okay. So what was Vd from that? It was basically 2I0 by GM1, which is how much? How is it related to this? How much is 2I0 by GM1? What is the expression for GM1? What is the most convenient expression to use here to compare? So GM1 itself is 2 times I0, which is the operating point of M1, divided by Vd sat 1 at a current of I0. Okay, so basically you get Vd sat 1 at a current of I0 from the linear picture, and here you get Vd sat 1 at a current of 2I0. Okay, does it make sense? Which is larger? Which one is correct actually? I mean, this is the actual nonlinear analysis, right? So what really happens is the currents don't vary like this. Okay, the current as it goes, the slope itself changes, and this is the point where it switches to 2I0. So this is Vd sat 1 at a current of I0, and this is Vd sat 1 at a current of, this is just to know, this is more for circuit analysis, and there is a square root 2 difference between the two. Okay, so you just need to know this, but it's okay if you use the linear model for our calculations, for our estimates. The important thing is to know that with a large enough input difference voltage, one of the transistor cuts off. Okay, so it's very important to understand this single differential pair, because this will be used for every op amp. Okay. So this only changes the amplitude at which the circuit starts fully slewing. But anyway, the whole thing is nonlinear, and it's very common to use the linear incremental picture around the operating point. Okay. Any questions here? What else is there to calculate? So these are the sort of just the I would say deterministic parameters. Now I have mismatch and noise, I think, which you have actually already calculated in a way in one of the earlier assignments. Okay, how would we calculate the mismatch and noise? And we do this for DC, we don't worry about the capacitors. I'll assume that the output is terminated by a voltage source, which keeps all the transistors in the correct regions and so on. And we look at the current that flows out. This is a lot easier than finding the output voltage. Okay. So now how should I calculate the effect of noise and mismatch? What should I do? How would I calculate the effect of mismatch? What should I do? So basically, both mismatch and noise effectively can be represented by additional current sources. Okay, I'll call it IN0. Only difference between noise and mismatch is the value of these current sources. That will work out later. Okay. So what is the, and we can now, of course, once you have these current sources, it is small signal incremental analysis from these current sources to the output. Okay. So how much is the output current? This is what we have to find out. How much is the output current because of IN0? That is the current source in parallel with M0. How much is it? Why? So basically, when you have this shorted, basically this current gets split equally between M1 and M2. Okay, I think if you have not, I think this was in the first or the second assignment, right? So this gets split equally between M1 and M2, and then whatever is going through M1 will get reflected, and current through M4 and M2 will be the same, and the difference will be 0. Okay. So the tail current source doesn't contribute to the differential output. Okay, it contributes only to the common mode output. This is a very common thing. So this is something you can remember as well. Okay, that is in this particular circuit. Now what happens to IN1? What happens to IN1? So if I have IN1 here, where does that flow? How would you analyze this? Maybe let's do the other two first. IN4, what will be its contribution to I out? How will it appear as I out? What is it? Where does it flow? By the way, I mean, by now you are used to this. You have to, of course, realize that this VDD means that there is a constant voltage source here, and for any incremental signals, that is a short circuit. Okay. So how does this IN4 flow? For this particular case, I will show the full current always flows in loops. Okay. This is something that you have to realize. In fact, a lot of the problems come when you have current flowing and there is no return path. Okay. So current always flows in loops. It may get split, combine, all that stuff. It has to, right? There's a joke about the electricity supply companies that they supply current on one wire, take it back on the other wire and charge you money for it. So that's, why do they charge money? They're taking all the current back. Huh? Okay. So what's the difference? They provided a higher potential, they get back at a lower potential. That's why they charge more. So anyway, this current, how does it flow? This also, let me complete the loop. It will flow like that. Okay. So what is I out as a contribution of IN4 to I out? What is it? Minus IN4. Okay. And what about IN3? How does IN3 flow? How does IN3 flow? So, where does IN3 flow? So basically, it will flow just through M3. Okay. But because it is flowing through M3, it gets mirrored. Okay. So the mirrored current will come out of the drain of M4, and you will have plus IN3. Okay. Right. So the currents through M3 and M4 will appear fully at the output. Now, what about IN2, for instance? How would you analyze what happens to IN2? Yeah, so you have to calculate that. Now, one of the tricks that you can use when you have current sources between two nodes, neither of which is ground, is like obviously, if you have IN2 between some nodes, you can always replace that by two exactly identical sources between the same nodes. Okay. And now this node can be tied anywhere. Why? Why can that be tied anywhere? There's no current flowing there. Okay. The current is identically zero, so it won't disturb the circuit, right? So now, if I do it for this particular case, what is a convenient node to tie it to? Yeah, invariably it will be ground, right? IN2, IN2, and this is grounded. Okay. So now the upper one, this one here, if you analyze that, by the way, you have to keep the same values for the two throughout the analysis, obviously. So if you look at how this current flows, this ground is here, right? So if you look only from the upper current source, IN2 flows that way, okay, right? And of course, this ground, the loop is completed through the ground. What about the bottom IN2? What about IN2, the other IN2 source? What will be its contribution to the output? What is it? Yes, Arka, what is it? What is the contribution? Which loop? It's not in a loop. I mean, this connected IN2, if I draw it more clearly, it is basically connected like this, right? So what is its effect on the output? Zero. Basically, it's like connecting to the tail node. By the way, this node I think you're familiar with. This is called the tail node of the differential pair. If you inject a current into the tail node, it will split equally and the contribution to the differential output will be zero. Okay. So this will not have any effect. So IN2 appears directly at the output. So you will have minus IN2. And similarly, what do you do with IN1? The one across M1. What happens? You can also split it into two parts and connect the middle to ground, middle node to ground. The bottom one will be similar to this, right? It will be injected at the tail, so its contribution will be zero. The contribution of the other one will be, it will get mirrored from M3 to M4 and come out. So you will have plus IN1. So once you know this, you can calculate the effect of both mismatch and noise. Is this okay? Any questions here? Yeah, I think those will add some minor details, but won't change the big picture, so we won't use them. Okay. Yeah, if you add GDSs and so on, some of the currents will get divided, but that fraction will be close to 1. It will be of the order of GM by, I mean, you will get expressions like GM by GM plus GDS, right? So it only makes the expressions messy without adding any insight. So this is a good enough approximation. But again, this is very important in any field of engineering. to leave out non-essential details. Okay, because if you put every detail at every step, you won't get any insight. You may be able to calculate some answers, but you have to be able to recognize what is important after some time. Okay, because yeah, GM is much more than GDS, right? Yeah. Parasitic? No, that is at this is at low frequencies. This is what it is, right? So basically, if the question is whether the parasitic impedance is admittance is negligible, so at low enough frequencies you can always neglect. So once you have this, what will be the spectral density of the output noise will be simply the sum of spectral densities, because these are 4 different components, they are uncorrelated. Okay. And how much is SIN1? How much is SIN1? 8/3. It's 8/3 kT GM1, that's all. So it's 8/3 kT times 2 GM1, because IN1 and IN2, their spectral densities are identical, plus 2 times GM2. This is the thermal noise contribution, and you can also add the flicker noise contributions. So basically this will be 16/3 kT GM1 plus this is GM3. Okay. This is the output noise spectral density due to the thermal noise alone. Okay. And flicker noise also you can add. You will get, what was the expression for flicker noise spectral density? Some K, and this can be different for NMOS and PMOS, right? So Kn times ID by L square. What is ID here? I naught, the operating point current, by the length of the NMOS transistor, okay, plus Kp I naught by Lp square, that is basically the length of the PMOS transistor, okay. Right? Is that okay? Now, for many circuits, and in particular for op-amps, this we also discussed, it is common to refer the noise to the input. Okay. So essentially, especially for op-amps, because they're always used in feedback loops, this is what usually makes sense. Okay. So you can represent the noise of the op-amp. If you look at the data sheets also, actually now you know all these specs, you can go back and look at the data sheets of the op-amps and see what all these are. So you can refer it to the input, yes? Right, yeah, because one from each transistor. Yeah, that's correct. So if this is the flicker noise from each of M1 and M2, you have to double that. And similarly for M3 and M4. Huh? No, this noise expression is correct. The spectral densities are all you substitute. What will be the input referred noise now? Let's again go with only thermal noise. The other one you can calculate if you want. It's not difficult. Huh? So this output noise divided by what? What should I divide by? Yeah, what is it? GM1. Okay, here we have calculated the noise spectral density of I out. You have to look at the transfer function from VD to I out. What is it? GM1. Okay, so the output divided by this square. So basically you get which okay. Now, why did I write it like this? Actually, this part, this you can recognize immediately if you had used the other form, right? If I refer each MOS transistor's noise as referred to the gate instead of the drain current, what would it be? It's 8/3 kT divided by GM1. So you have 8/3 kT by GM1 over there, and the other input transistor also has 8/3 kT divided by GM1. Okay, so that is like having two uncorrelated noise sources in series with each input, okay, of the op-amp. And this can be substituted by a single. You get exactly the same thing, right? You sum these two, and then you put either 8/3 kT by GM1 on each one, or 16/3 kT by GM1 on one of them. You will have the same result. Okay, because you have some input, the actual input, that if I take it in this polarity, what will it be here? This plus these voltage sources, right? So the sum of these voltage sources is the total input referred noise. So you can see that right away. I mean, this part will come out, and you actually have a small degree of freedom here. If you make GM3 equal to GM1, all four transistors will contribute equally. But if you make GM3 smaller, you can reduce the noise contribution. Okay. So this is this first part here. This is the contribution from the input pair, and this you can't avoid. If you make the input pair with a certain transconductance GM1, you will get this noise. Okay, this is like if you have a resistor of value R, you will always have noise current 4 kT by R associated with it. Similarly, if you have a differential pair where each transistor has a transconductance GM1, you will have an input referred noise of 16/3 kT by GM1 with it. Okay, and you can't change this. Of course, you can reduce, I mean, you can increase GM1, but this will change so many other things, right? Because GM1 is the primary parameter here. The unity gain frequency will change and so on. Based on that, you may use some GM1, and if you use that GM1, you will always get this noise. Now, this part, this is due to the mirror, and this is in a sense overhead, right? I mean, in principle, you can make this negligibly small by making GM3 very, very small. There is no reason to have a large GM3, right? All you want is a current mirror. You can use any GM3 you want. But what is the cost of making GM3 very small? Size? GM3 very small. So GM3 is, the current is the same, M1 and M2, right? 2 times I0 by VSG3 minus VT. Okay. So now the only way, I0 you cannot change because that will change GM1 also. The only way to change GM3 independently of GM1 is to increase VSG3 minus VT. And if you do that, you will have more voltage across those transistors and your swing limit will be compromised. Okay. This is okay. Anyway, go back to the assignment problem to just refresh the analysis if you are not familiar with it. But it's straightforward, and this kind of thing is used very commonly. By the way, this especially this single stage op-amp results, please work them out by yourselves, because every time we have this circuit, we are not going to sit and work it out. We will just use the characteristics we derived here in all the future op-amps, and every op-amp will use this. Okay. And quickly, what will be the mismatch? So from this, ideally, when VD equal to 0, the output current must be 0. Because of mismatches, it will not be 0. Okay. So what will be the variance of the mismatch current? You have to add the variances of all these. That's all, right? And what is the variance of each of these? This is the variance of I naught. That is the absolute value. Okay. So what is the variance of let's say IN1? The current source across the MOS transistor. What is the variance of that? So it is sigma VT1 square times GM1 square, right? So that is the variance because of VT mismatch plus sigma beta 1 square times the nominal drain current I naught square. Okay. So using this, please calculate the expression for the variance of I naught. Okay. And similarly, that you never specified as an error in the output current, you will always refer it to the input. That is what is called the input referred offset. Find the variance of the input referred offset. Okay. Any questions? Right. No, no. The sum has to be the same. Then you can vary them any which way you want. No, no, it won't, right? Because the op-amp reacts to the voltage here. The actual voltage is something. The relationship between the actual voltage and the input across these terminals is defined by that. Whether you put it here or there or both, it doesn't really matter.